stream started, finally. And there's the cat coming downstairs, right on cue. If only the camera was in focus. Hey, cat. What do you think we're working on today, Tuco? So I hadn't been streaming much this week because I had a lot of kind of boring boilerplate work to get through in order to get a new experiment set up. But I think we're finally ready to do some interesting stuff with that. All right. Hello again. So this is, whoops, camera. Where did you go, camera? Did you lose power somehow? Pardon the technical interruptions. Okay. Also, the cat is, oh geez. I've been having so much trouble with this arm the camera's on. Man. I think I need to actually tighten that. Oh, are you not getting any sound? Looks like we've got sound. All right, thanks for the warning, though. I appreciate folks keeping on top of that and letting me know when something might be wrong. Oh man, yeah, I know this is a bit of a tangent, having to fix my camera gear, but this will make things a little better. Is that good? Yes, I just got back from the International Space Station, clearly. No, this is like an old flight suit that I got due to its flame-resistant properties for something a while ago where that was necessary, and it's also just kind of a convenient thing to wear around the shop sometimes. Oh man. This camera arm is so nice, but it's also really starting to get on my nerves when it doesn't work out right. Well, so I'll probably try to explain this a little better once I actually have stuff on camera, but just so that this isn't quite such a mystery at the beginning of the stream, this is going to be a continuation of the voltage glitching to extract PLC firmware project. And that one hit a bit of a snag where I bricked the hardware I had, and so it's not necessarily something I have to deal with now because I do have a spare board here, but I took some time to investigate the way it was bricked, and it seems like it's still running like vendor-specific code. It's not stuck in some kind of boring bootloader. I didn't just like completely blow away Flash, it seems. And that vendor-specific, well, and I don't know whether it's a proper bootloader or whether I've just crashed the firmware somehow very early on by damaging the chip. But regardless, I've discovered that in this broken state that it's in, it is reading the file allocation table off of an SD card if one is present. So my plan is to run an experiment where I pretend to be an SD card and just give it a whole bunch of fake file names. And so, you know, this might even be fast enough to search them exhaustively, but actually that would take a while. So I think what I can do is, in fact, use side channel analysis to watch the code run through the file list and do a bunch of string compares, and then look for changes to those file names, which cause the string comparisons to take a little bit longer, and then I know I've gotten a little bit closer, like what, I can step through it digit by digit. So that's my plan. So I had to do a bunch of work to get an SD card emulator into a state where I could use it for this. And so I'll talk in detail about what I had to do for that, but a lot of that involved learning some new hardware design tools, which I've been pretty happy with. Oh yeah, there's what happened. The ball bearing skipped over into the adjacent track. That was not something I could solve just by changing the pressure. Yeah, so there's basically a suite of tools for designing complex hardware, and especially system-on-chip designs in Python. And it was originally designed for this open source kind of video synthesizer project called Milky Mist. But then that Python-based hardware description language evolved into its own thing that's pretty powerful, called MiGen, M-I-G-E-N. And so that thing is pretty awesome. And even further, there's a, man, this thing is annoying. There's a project called MySock for System on a Chip that's based on MiGen, and that one, it includes a couple of CPU cores, and then it has ports that describe how to access the memory and, how to set up a bus and clocks on various dev boards. And it actually does some really nice stuff to make the process of actually connecting all the stuff on your system on chip together really painless. So that's pretty cool. And then, so it's like a combination of factors. It's, man, this thing sucks. It's, I think the ball bearings are all still in the right spot. I just have to kind of line this up right when I put this back in. And then I think I just have to tighten this bolt exactly the right amount. That sounds terrible. Oh, man. Oh, this is promising. Oh, yeah. Okay, maybe that was just it not being tightened enough. So maybe now I get it into the closed position and then tighten it as much as I feel like, and then how does it open? That seems all right. Okay, let's see if this works. I am so done with messing with this right now. Anyway, yeah, so this MySock thing is actually pretty awesome, and it supports a couple of different CPU cores. Currently the OpenRISC core, which I have not tried yet, and the LM32, which is an open source core made by Lattice Semiconductor for their FPGAs, but it's generic enough to use on whatever FPGAs you want. So that's been nice. It's got a decent enough GCC port. Oh man, can I get this out of my face too? It doesn't always have to be right in my face. Okay. Thank you for bearing with me for another surprise equipment maintenance moment. I think that helped a lot. Let's put this greasy wrench back. All right. Oh, I was just catching up on chat slightly. Alex says, I'm still trying to imagine a project that requires flame-resistant clothing. Well, that's actually related to the logo on here. So it looks like DDR, but you'll notice it says Dance Dance Emulation. This is some friends of mine a while ago made this thing that was like DDR, but when you get something wrong, it shoots you with the fireball, and so then you have to play it using like a fireproof suit. And so this is not nearly enough protection to actually play the game. This is the protection that I wore to help run the game, because I was like running around with a torch on a stick, relighting pilot lights, while other people were in much heavier suits actually playing the game. So that was a weird project. I only really, I didn't like build the project, I just helped run it once, but I still ended up with a patch, so it is what it is. Oh, and then, oh yeah, and then also a mention of Bunny analyzing SD cards. Yeah, there's actually, I think it was Bunny who had a really great blog post on like one particular series of SD cards and then kind of tearing them down to find what microcontroller was inside and reprogramming them. And yeah, I mean, it's, when you set out to build something like an SD card, you're not going to implement everything in hardware. You're going to choose some kind of hardware-software boundary and then stick a microcontroller in there. So there's going to be firmware somewhere. Yeah, so wanted to show off these cute little critters. I found these online. I forget exactly who was selling them. They came up on an Amazon search, but I needed some kind of breakout since I didn't have anything that was the right thickness to shove into a micro SD card socket anyway, so I needed some kind of adapter. Focus. So this has a full-size SD card slot, which I'm not currently using, but is nice if you just want to pass through, and then a place to put some 0.1-inch headers, and then it is shaped like a micro SD card on this end. Come on, focus. Do we need to stop being servo AF? Let's be less servo AF right now. Oh man, have I had too much coffee to hold this steady? But yeah, that's kind of what we think. This, well, so this LED here is just connected to the SD card power, but that actually turns out to be useful since most readers will just power on the card when it needs to be accessed. And so, you know, before I got the emulation working, I could see this just kind of pulse as it was trying to initialize the card, but now it stays on steady. Yeah. Oh yeah, Nicholas points out there's also a CCC talk about the SD card reverse engineering. Yeah, I think that sounds familiar. I think I watched that. Okay, so this is the, let's focus on this new setup for a sec and put this aside. This is the currently bricked thing we're going to be working on in just a sec. But right now, this is my little development rig. So I've got, oh, another bad camera angle. I just feel like I'm rolling the dice every time I clamp that camera. So just a USB hub and a compact flash, or USB hub and an SD card reader, and the logic analyzer, which this is a Salier Logic 16, which is not really fast enough for an SD card in a modern reader, but it's, I found an SD card decoding plugin that's open source, so I was using it for some decoding. So it is kind of useful, but we're probably going to switch over to the O-scope in a sec because this is hitting its speed limits, and I need to start evaluating the timing of this thing. So, hey Tuco, cat's back. Tuco, what do you want, little cat? Those are headers, those aren't cat toys. All right, so on here, this board here is a Papilio Pro, which is a pretty low-cost FPGA board. These are pretty nice because it has, you know, so this FPGA is a Spartan 6, which is not the most recent or the hugest, but it's plenty enough for, you know, getting started, and it's just barely big enough for this particular design. So we have an FPGA, we have 8 megabytes of RAM, We have an FTDI interface with 2 ports so that it can be a serial interface and it can be JTAG for programming the FPGA. And nothing on the back. So it's a pretty handy little board. It has little shields that can plug on top that they call wings. And you can either use the whole thing as a mega wing, or each of these little 8-bit ports are named sort of individual wings. So I just made a little breakout for one of the wing ports. And it's also a pretty nice board if you're kind of new to FPGAs, because they include like literally it's a modified version of the Arduino IDE that lets you do both code and circuits. So it'll synthesize a system on chip in here that includes a CPU plus whatever peripherals you want, and you can draw a schematic diagram connecting the peripherals and then write code in the Arduino IDE that gets bootloaded onto they use a ZPU Ueno processor on here. So that's a pretty cool dev environment. I played around with it some. I'm not using it for this project, but it was really interesting to check out. And definitely seems to be something I might point people to if they're new at FPGAs and want to kind of play around with the upside without having to set up the entire infrastructure. But of course, that said, I really like the experience of using MyGen and MySock so far, and it also takes away a lot of the pain that I've gotten used to from FPGAs, so I might recommend that people who are new start with something like that too. I mean, it helps to understand the layers underneath, but it's really nice to avoid some of the drudgery associated with just kind of doing the same thing over and over again, since traditional hardware description languages like Verilog and VHDL provide very little abstraction. You can do some abstraction, but even like data structures aren't really a thing, so it gets tedious. Okay, so I think I'm going to go to the laptop and actually look at how we've got this system on chip designed. And so I'm going to start by just showing what I've got so far, but I think I'm actually going to need to add some new code to this today also to make a small triggering system. Right now I've got this set up so that this FPGA is programmed with 2 main things on it. It has a CPU core and an SD card emulation core. The SD card emulation core is actually doing a lot of work in hardware, probably more than even a regular SD card would. It processes all the SD commands in a hardware state machine, and then you end up with a set of dual port RAM buffers, which have one port facing this SD card emulation state machine, and the other side of that you can choose to hook up to whatever. In this case, I've hooked it up to the bus of this CPU core. So I can write code in an interrupt handler to check to see what block the hardware wants, write it to that SRAM buffer, then tell the hardware I'm done. And that's basically all it's doing. Okay, let's get a VM. Where the heck is my screen? I guess that's where it decided to put it. Okay. So the Xilinx FPGA tools will run on Linux or Windows, but it seems much easier to set up the MySock tools on Linux at this point, so I've been using CentOS. Still not without its yak shaving, since anytime you distribute like binary software under Linux, it's going to have dependencies that are tricky to port across Linux distros. So I ended up basically choosing the distro by compatibility with the Xilinx tools, but then it's missing a lot of the bleeding edge Python stuff that MySock needs, so I have to compile that myself. All right, let's take the camera off the screen, maybe. this not scaling? Don't know why my Linux is not changing screen resolutions. I think I might have broken VMware Tools during suspend and resume. Let me just freshly boot this VM, because there's a lot going on here anyway. Hey, Chico. Where are you at, kitty? I thought I just heard him around here. Yeah, this software, I mean, FPGA design software, at least in my experience, has been pretty notorious for being really annoying in pretty much every possible way. Being buggy, being giant in terms of download and system requirements. So that's why it was kind of a nice breath of fresh air to try out the open source FPGA toolchain. Ice Storm and friends for the Lattice Ice 40 FPGAs. But this project needs something a little larger, so I'm using the official Xilinx tools. Meow. Wow, good jump, Took. That looks better. Yay. Okay. Let's also, I guess, have a web browser, since that might be useful. Oh yeah, so there's some good references to check out here. So cool. So MySock is the project we'll be building on. We also want this, which I'll explain in a sec. And then this is what we are currently building. So, because I need at least half of my projects to have whimsical names, this one's called FlipsyFat, because it's a fat emulation that's designed to let you flip through files until you can find the right ones. So I've already got this kind of work in progress on GitHub. It doesn't do everything it needs to do yet, but it's certainly already got some interesting pieces that might be reusable. And then, so this is the actual system on chip, MySock. And so if you're looking to get started with this, basically all you need to do is buy one of these Papilio Pro boards or something similar. I mean, if you want to run your design on real hardware. And I think this board was like $80, so pretty cheap as far as FPGA boards go. And then this mostly has the instructions you'll need to get started. I had trouble with a couple of these things. Like I had to recompile GCC a few times with different options, since disabling libgcc turned out not to be a good option. I should send in a patch about that. But yeah, mostly the getting started instructions here are pretty good. And so the other thing we'll be building on is this, which has no description in GitHub. Let's see if there's a different description page. I found this, I was just searching on the internet trying to find SD card emulations to see if I could get away with not having to build something totally from scratch. And so I found this based on somebody mentioning it on a forum post somewhere, but Google has a pretty decent, oh man, maybe they don't have a good thing about their actual reference platform, but I think they have a page for Project Vault itself. It's kind of an interesting project. Is it not a thing anymore? Did they delete it? Is it just not on Google? No. Well, here's some press about it. I guess you get this idea. So I don't know why it doesn't have an active website. Like, maybe it's not a thing anymore, but this stuff seems relatively recent. This article is from the middle of 2015. Anyway, their idea was this is like a secure computing peripheral that you build into an SD card, since pretty much everything now has an SD card slot. And so it was an interesting idea. But then the thing that I came across was this ORP, which, despite having no documentation really, I eventually find this means Open Reference Platform. And so this is basically a hardware design that they published that is one feasible way to implement something like this. And so it doesn't seem like it would be nearly small enough to fit into those artist conceptions, but it does seem like it would work. And it's actually really complicated if you go through here. I mean, it's a system on chip, as you would expect. It has a processor core. In this case, I think they used OpenRISC. They call it the M-cell system on a chip. I forget what M-cell stands for. And I think Geophyte is the name of the development board that it runs on. So yeah, so here's like the root of the actual hardware for their design. And so it has some of the stuff you'd expect from a system on chip, booting and clocks, and this connects all the pieces together. Yeah, OpenRISC 1000 CPU. So this is what actually instantiates the CPU, which is in another file, connects it to things. If you haven't seen this before, this is Verilog, which is one of the two most popular hardware description languages, the other being VHDL. And it has kind of a C-like syntax, but it's not describing code, it's describing hardware. So like if it says, x equals y plus 2, it's not an instruction, it's saying that x is a signal that's the result of an adder that adds, y and 2 together. So it's a bit of a paradigm shift, but I like it. So anyway, they have a couple of interesting peripherals. There's a true random number generator, which is pretty simple. It actually looks so simple that it's like, how could this possibly work? But they cited a paper about it elsewhere, which I've been meaning to read. It's like a free-running shift register-based oscillator kind of thing. But anyway, the two interesting bits here are peripherals called FOFS and SDHC. And so FOFS is actually what the CPU communicates with when it wants to pretend to communicate with, with the host device that the SD card is plugged into through some magic files. So this is actually a hardware device that generates a fake file allocation table and a fake partition table and all that. And I guess it helps to know that within their fake SD card, they've broken that into two partitions. There's one that's actually backed by real flash memory. So in addition to their fake implementation, there's also like, a NAND interface and a flash translation layer for actually backing that by real flash. That's just so that you can store a small amount of data on this thing. And then this FOFS thing actually implements that other partition entirely in hardware and gives the CPU interfaces for reading and writing individual blocks. So I was just noticing a comment in chat about two other HDLs called MyHDL, spelled MYHDL. And that one, I looked at it really briefly a while ago and didn't end up using it for much. But yeah, it's very much in the spirit of this. I really like some of the design choices they've made in MyGen. I don't know, you'll see. They really make it easy to connect things together with very little overhead. Kind of a very Pythonic way of building hardware. So this original ORP design actually does a lot in hardware. So this FOFS, for example, there's a ROM. This is the master boot record, which gets compiled into actual logic gates. This is the FAT header, which also turns into actual gates. This is doing the arbitration for connecting all the memories together. So you can see that there's quite a lot of just boilerplate code to, this most of what this module does is just connecting some ROMs and a couple of RAMs onto a bus. But not really much of that is semantically expressed here in Verilog. Whereas when we take a look at the MySoc code, we'll have Python objects representing the type of bus interconnects, and those objects can actually generate a lot of this code on behalf of the modules. So anyway, I ended up not using any of this FOFS code. If you look at, well, I guess it's still in here. If you look at this other module, SDHC, I used some of that. So there's a lot in here. There's a flash translation layer, which is what takes a raw NAND flash device and makes it look like kind of an idealized block device. Then there's the actual NAND flash implementation, including error correcting codes. Then this SD collection of modules, that's the actual stuff that implements everything else. VRAMs are some wrappers around device-specific, well, not device-specific, but this describes a RAM. Like, this is how you would describe the way a memory works in Verilog. So this is saying that, when a clock edge occurs, the write signal tells you whether, we're writing to memory, and in that case, this is how the data flows. And if we're not writing, we're reading, in which case this is how the data flows. But this module just exists to create a memory that has the very specific, widths and any other characteristics that this module needs. So, I have better ways of doing that kind of thing. But the two modules that really matter here are this link layer and the phi, and then to some extent this manager layer, which is just a little off this, or no, it's right here. So phi is what actually drives the SD, what actually drives the signals on the port. So you can see here, these actually match up with the wires you'll see on an SD pinout. I think we'll get into the SD protocol a little bit more later, but it basically acts like, it's a little bit like SPI, but you have some aspects of it are a little bit more like asynchronous serial. You have to worry about start bits, and there's kind of a packet framing. And there are basically two separate serial buses. There's a 1-bit bidirectional command bus and a 4-bit bidirectional data bus. So the data bus is only used for the actual contents of data packets. So in this phi, that data bus really gets routed straight into the RAMs here. So these are signals that would connect to some external chunks of memory. These are all the signals that you would need to read and write from a buffer of 128 separate 32-bit words. And so in here, this is actually just generating those signals. Let's see if we can find one of those. Oh man, I've lost all my keyboard muscle memory from using Mac and Linux simultaneously on this machine. So these block RAM signals go out externally to the memory that it expects to see. So then here you can see this data input FSM. This is a finite state machine that just handles moving data back and forth between the serial and parallel, or between the serial bus and RAM, where it's going to be parallel in 32-bit chunks. So here it's actually shifting in bits of data, computing the CRC as it goes, accumulating it in a buffer that eventually gets flushed out to memory. So that's just a dedicated hardware machine that just takes data and moves it from the serial data bus to the memory. Commands don't get involved. Commands turn out to be a totally separate state machine driven by a totally separate bus. And so the phi acts as an adapter that takes this SD card bus with its command and data portions, and it splits it out into two separate parallel buses. There's a parallel data bus that's formatted such that you can directly connect it to some SRAM. Then there's a parallel command bus, which is formatted to attach to an external state machine for processing those commands. So that external command state machine is this SD link layer, which I'm also using. So this is one of those design decisions that made me kind of go WTF when I was looking at this at first. Because, I mean, I guess it's fine if you're not optimizing for size, but the way they represent these commands is by passing these huge shift registers between the phi and the link layer. So this, so you can see here, there's a response output register, 136 bits. There's a data register, 512 bits. Command, 48 bits. I think what they were thinking is that this is all designed to hold the largest possible commands, and most of the commands just fill a lot of that with zeros. And I think they're assuming that the hardware optimizer can remove some of that, or they just don't care. Either way, I'm not too fussed about it because it fits in the FPGA I'm using, but it definitely is not an especially optimal solution. But it's pretty easy to use. Effectively, this link layer state machine just gets these huge wide packets that have, this is the entire command that we just saw come over the bus, and then here's a strobe that says a command is happening, and then the state machine just gets to process it and then signal when it's done. So the state machine here actually takes care of, you'll see it shortly, just processing actual individual commands. So yeah, here's the reset command. Here's sending the card identification word. There's various ways of reading. There's like individual block reads, there's burst reads, and this handles all of them. So here's, command 18, read multiple. Command 17, read single, is the one that I'm actually going to be seeing from this device that I'm trying to unbrick. So it's actually the simplest kind of read. You can see generally how a command would be processed in the domain of this hardware state machine. And none of these are instructions. These are all declarations that something happens under a certain condition. So this is saying that when the card state is command 17, or when our command is command 17, and the card state is that we're in a transaction, and this condition is true that the command in argument isn't out of range. Under all of those conditions, then these get wired up. So effectively, if you look at the wires associated with this signal, they will be driven by a multiplexer that selects either this value or whatever other values it might take on based on these conditions that are set up by the enclosing statements here. So, and that's a little bit of a lie. There are some limitations to how that reaches, or to how far that reaches in Verilog. In Verilog, there's kind of a notion of, I'm trying to find it. So this thing that says always here is the beginning of like a separate process in Verilog, which has some linguistic constraints to it, but it doesn't actually mean anything as far as the hardware is concerned. In the hardware, this all just kind of happens simultaneously. So you can see there's a lot here. I'm glad it fit on the FPGA, but it does. And in the original Project Vault, the way they used this was still really complicated. So the link layer and the phi, those two things together were responsible for handling commands and moving block data, from the actual serial data bus in and out of RAM chunks. But they didn't, those two layers on their own don't do anything to put more data into those RAM chunks, and that's something you have to do really fast if you want to keep up with the SD data rates. So you actually, to have a usably fast SD card for just general purpose data storage, you really want to have some hardware that's then taking those little tiny single block buffers and quickly shuttling those to some larger data storage. So, basically a DMA engine. And in this open reference platform designed for Project Vault, this was actually really complicated. So this manager layer is basically a DMA engine that works on behalf of the SD link layer and SD phi. And the manager then grabs blocks from this external this external bus interface, which I think is a wishbone master. How does that work? I think that's what these are. So I think this ext read-write interface here is a wishbone bus master. So basically this acts like a DMA bus mastering device that just sits there and shuttles data between those tiny little blockrams and some external device that knows how to store and retrieve data blocks at a time. And so you see that a lot of this is actually getting complicated because it has to do a little bit of caching, since the SD card peripheral wants that data there right away. If the data isn't in the block RAM the very cycle we need it, then we have to stall the response, and that slows down the SD transfer. We basically end up kind of going back and forth between two modes where either whatever it is that's filling those RAMs is doing some work and the SD host is making no progress, or the SD host is reading and the other end is making no progress. So this ends up doing a lot of work to, first of all, double buffer, so it has two separate RAMs, one for the SD interface to use and one for this bus master to use. And then it also tries to read ahead. So if it looks like there's a burst read happening, then it'll actually read the next block before it's being requested. So this gets complicated. There's a good reason for this to be its own module. And then behind that abstraction layer of another bus, so this then requests blocks from a whole host of other peripherals, which can be connected using this wishbone standard bus interconnect. So that's how they implement both the flash translation layer that goes off to real flash memory and the fake FAT that just has files that get directed to software. So that's my understanding of how this original project worked. So I stripped out a lot of components to do my own thing. So if you look at what's going on here, actually I'm going to switch from GitHub back to the virtual machine since that's a little nicer. All right. Oh, that is too many windows. Let's close some of these. Okay, I don't actually want this window. I do want this one. Can we make this a little bigger? I don't really know any of the keyboard shortcuts for the Linux version of Sublime Text yet. Is that the same? Okay. Cool. So now we're going to be in Python land for a bit. Oh man, this font is not amazing. Oh man, I don't really want to have to fuss with that right now. All right, so where to start? I guess we have a README, but you've already seen that. Really, I guess I usually start with the makefile. So there, you can see a few different things this is doing. So we've got synthesis, then flashing the synthesized hardware design into the flash on this board, and then a couple of different software experiments to build, which have their own makefiles, and a lot of annoying arguments to pass in. So really, the hardware all just starts here in this target-specific Python file. So in MySock, it's pretty easy to do out-of-tree builds now because you can basically just make a Python module that defines. So this is defining any kind of board-specific, any board-specific classes really. And then I also have a main program here that actually just builds the entire system on chip for that board. So if I run this Python file, then it'll actually just start compiling this hardware. So I can just do, oops, let's see, targets, Papilio Pro, which is this board I'm using. So it pretty quickly runs through the Python, and then all the rest of this is the Xilinx toolchain building the FPGA image, which takes like 4 minutes on this machine. So, so you can see a lot of this is just kind of boilerplate that's designed to be extensible. Here is where we're actually kind of attaching all the hardware together. And there's also a pretty nice system in MySoc for defining board-specific hardware resources that you can grab by name. So, for example, I can define this SD card port here, and I can say it's got a clock signal, a command signal, this data bus, and then from then on I can refer to everything here by name and not have to worry about where stuff is attached. And likewise, these don't even have to be actual pin numbers. These are references to pins on a connector, which was defined in, well, let's open that up, because that's actually kind of interesting. At least I think it's interesting, the definition for this particular board that I'm building on. So that's in MySoc, or no, it's actually in MyGen. No, it's in MySoc. There's actually board-specific stuff in all 3 packages that all build on each other. So there's like toolchain support in MyGen itself, and then there's support for this board in the system on a chip design. So that'd be in MySoc targets, and then let's just open this. And then Papilio Pro. So here's like a module that handles clock rate generation, which we'll skip over now. Then the system on a chip inherits from another subclass, which was the basic system on a chip plus SD-RAM support. This defines a few new things that are specific to this bus, like the address where the firmware gets loaded. Since the firmware and the FPGA image are in the same SPI address space, this ends up depending on the size of the FPGA image. So it goes here. This adds the physical layer interface to the SD-RAM. Optionally adds an interface to external ROM, unless you have internal ROM. So over here in my code, I just import that and then subclass it again. And I can mostly just add my SD card emulation module. So this debug stuff is totally optional. This actually, you can see how this I/O request system works. So I'm just getting an object here which has all my debug ports in it, and then I'm adding combinatorial logic to this module. So this will make maybe a little more sense. I mean, at least for me, this made more sense after reading through some of the example code for MyGen itself, because this actually is just specific to how it represents logic in Python. So anytime you create some kind of expression, it sort of just like in functional programming, unless you use it somewhere, it doesn't really exist. So the way MyGen achieves this is that each module, which is something that you can instantiate in your hardware design. So in this case, this derives from a base module, so this, by extension, is a type of module. And all the modules then have some basic features that include combinatorial logic, synchronous logic, which is something that happens on a clock edge, a clock domain that says when that synchronous logic happens. In this case, the combinatorial logic just acts like plugging 2 wires into each other. It isn't, it isn't actually introducing any additional registers into the design. So this is just how I'm attaching this debug output port to monitor some signals inside the SD emulator. So one thing that I really like about this relative to Verilog is that in Verilog, if I wanted to pull out these debug signals, I would have either had to go add a bunch of plumbing to my Verilog module just to get all of those wires out, or I would have had to already have all the debug signals there, just pre-expose anything that I might want to use. Either one introduces a lot of annoyance. So in this case, I can just go into that module's attributes and get the signals I'm interested in. So then this is actually all the glue necessary to add my new SD card emulator into the system on chip. So then the SD emulator is another one of these hardware modules that I'm instantiating and attaching it as a submodule. Just like I requested the debug port down here from my I/O up here that I added to the platform, I am also requesting the SD emulator port. And then most of the rest of this is for attaching the hardware to the system on chip bus so that we can access it somehow. So register mem attaches, it basically attaches something as a wishbone peripheral. So if you haven't heard of wishbone, it's just a really simple bus standard that defines a set of signals that two hardware devices can use to communicate about memory accesses. So if you're building a system on chip, it's just the glue that you would use to attach all the peripherals to your CPU. So all the RAM would be connected, all the ROM, all the I/O devices. In this case, there's kind of a centralized special purpose memory bus for all the registers on the system. And this is actually super convenient. It does a lot of automatic generation of status and control registers. So that's why it's CSR. Control and status registers are totally automated. You can just instantiate them and attach them to one of these Python modules. And then if you have a mix-in class that searches for those, then you don't even have to register them separately. So that's what I'm doing here. We'll take a closer look at that in the actual SD emulator, but this just tells the system on a chip itself to look for registers inside the SD emulator module and hook them up to the main centralized register bus. Similar with interrupts, there's a centralized interrupt manager, and this just allocates an IRQ for our device. And these are also nice because since this is like a build system effectively for both the hardware and all the boilerplate software, this builds header files and BIOS images that we need for the system. So for example, just by adding this to the interrupt devices, if I go down here into the generated include files, I think this is what I want. Yeah, so here's some constants for, you can see I've got a UART interrupt, a timer interrupt, and an SD card emulator interrupt. And they've got some accessor functions. And so all of this is automatically generated from the Python code. These are all registers that were just, they just took one line of Python code to declare. And now I've got accessor functions and memory addresses and all that. So I'm pretty happy with that. Similarly, I allocated this memory address myself, but just by adding it to the memory map on the system on chip, we get a header file. Where was I? So yeah, that's the memory address that I chose pretty much arbitrarily up here. It's not totally arbitrary. It's kind of limited by the way the decoding is set up, but if you know how the decoding is set up, you can allocate memory addresses pretty much arbitrarily. Register memory is, why did I open just the targets directory? So there isn't a lot of documentation for this stuff, but I found the code fairly easy to grok, so that's usually a good sign with Python. So here's the system on chip core that we're inheriting from. You can see a lot of the basic stuff that we build on. It includes a UART, ROM, RAM, a timer. So then this thing where we register mem, that adds a memory region to the memory map. And then this add WB slave thing, that adds a wishbone slave to the memory arbiter so that all the devices which act as wishbone masters, in this case the CPU's instruction and data cache, they can end up fetching from this device just like they could end up fetching from anything else. So let's go inside the CPU or the SD card emulation core here. So this is another module. This auto CSR means that it's just searching for any instances of these CSR-based classes and adding them to a list automatically. These turn into the registers that we can see in the header file. So for example, this will get combined with the name of the parent class, which in this case is SDEMU. And then it'll just turn into SDEMU read activity. So we can also see that in the header file here. So yeah, automatic address, some header, some pound defines here, and an accessor function. So, and then these classes themselves are actually pretty straightforward too. So over here in MySock again, those are in CSR. So there's like a general purpose kind of CSR, which you can, it's basically like a very, very tiny bus interface. It just gives you like one register and like a read and write handshaking interface. So yeah, you can see that here. The terminology is a little bit weird. So R is the data that is being written, and then RE is like a write enable signal. So I don't know why they chose those names, but you can basically hook those up to whatever you want. But for simple use cases, it's pretty common to just have a register that you want to read or that you want to read and write. So this creates simple registers for that. And all of these can be any number of bits. So it can be 1 bit, it can be 64 bits. I think you can even maybe make them larger than 64 bits, but it might not know how to do accessor functions. So a lot of this is just instantiating submodules. So actually, let's take a look at this SD link layer first, since this is actually the first thing I did. I just took that existing Verilog code from Project Vault and wrapped it. So I didn't end up modifying it all. I just subset it and then ended up writing some Python code around it. So these are the same modules from before. There's the phi, there's the link layer, there's some other stuff. There's synchronizers and constants, parameters. And so this is all like BSD licensed stuff from Google, or Apache license, similar. And then in this core file, SD link layer, this is my adapter. This could stand to be maybe a separate Python file. Anyway, so the interface that these modules come with is just incredibly verbose. Like if you want to instantiate these things, like look at what this, like if we go back over to Project Vault again. So their top level code is in this file. So this, ignore this stuff because this is how this is then interfaced to the layer above it. Just to get the link layer and the phi connected to each other. So we've got, well, that's the wishbone interface that we're not using. Here's a bunch of wires that we're declaring. But then this is just the declaration of the link layer. So we've got clock signals, a lot of stuff connecting between the link layer and the phi. Then we've got the block interface that goes off to the manager. So none of this is abstracted. We don't have any way of wrapping this. In Verilog, it's just this long list of things that you have to distinguish by name. So it gets super long and repetitive. Whereas over here on the adapter side, I've still got to deal with that. But once I've got one of these objects, then I can just reference these members however I like using kind of normal Python code. So, and a lot of this stuff I don't end up caring about externally at all. So a lot of these signals are just internal communication between the phi and the link layers. So down here, when I instantiate the phi, for example, I'm connecting this like data out register. This is an input on the Verilog module, and it connects to this wire. And then similarly, this is an output on the phi, and it connects to the same wire. So there's a bunch of that. But there's a few new things. So these are some signals that I expect the external module to use. Some debug signals that are exposed, some error signals, some adapters. I don't know why they use an active low tri-state signal, but this just creates an inverter to, excuse me. So MyGen has its own way of doing tri-state outputs, which are outputs that can either be pulled high, pulled low, or left floating. Because usually inside the FPGA, you don't want to deal with that because you want everything to be either 1 or 0 until it gets to the actual output buffer. Since that high impedance state is usually implemented, it's implemented in the actual output buffer. And so in the FPGA, usually you're not going to be using high impedance signals. So MyGen has a way of representing that, but needed a bit of an adapter. MyGen has a really nice system for clock domains. So instead of having to pass around clocks all the time, it usually has an implicit clock. Modules can just have like a set of clocks that they have, and there's a default system clock. But you can also define new clocks, and you can have adapters that let you cross clock boundaries. In this case, it was really convenient. Since, as I was saying before, the PHY really just has a little machine in it that's connecting the serial data bus on the SD card directly to the RAMs, so nothing else in between. That also means those RAMs are on the SD card's clock domain. So the actual clock I'm getting through the SD card connector is actually the clock that those RAMs are being driven by. And that's actually a really nice way to cross clock domains, because I want the other port on that RAM to be on this sort of main clock domain that my processor is using. So using a dual port RAM is a nice convenient way of doing a clock domain crossing. And it happens that with MyGen, you can implement that really smoothly just by telling the memory port what clock domain it's on when you create it. So here I'm using MyGen's memory primitives, creating the 2 buffers, which are just 2 separate blocks of RAM. In this case, it's 32-bit words and 128 of them, making a 512-byte buffer. And then I'm exposing these so that other modules can just attach stuff to this memory when they want to. But, subject to hardware constraints. You can just have as many ports as you want. Usually the hardware can only have like 2 ports. But this makes a pretty convenient way of, if I have memory with a spare port on it, and maybe I want that to be available, maybe I just want to be able to leave it unconnected, you can just have this memory object that you can pass to some other module, and then that module can create whatever kind of port that it wants. So in this case, I'm just doing that internally and creating this port so I've got an internal read port and an internal write port that are both on this clock domain that comes straight from the SD card socket. So then, now that I've got these ports, if this was Verilog, this would be like, how many signals? At least, so I've even minimized this a bit because these had a bunch of unused signals because the read port only reads and the write port only writes. So I don't even need the write enable signal on the read port, for example. But a fully featured memory port in Verilog looks like this. You just kind of have to cart around all these signals everywhere you go. It's like clock, address, write enable, and then everybody has different naming conventions. In this case, data is the data that you're writing, and Q is the data output, which is like kind of an old school digital logic terminology. Yeah. So in this case, I can just access internal read port .address, internal read port .read, .write, and attach them to the ports that the Verilog instance expects. So that's mostly what I had to do to wrap this. So now I've got this, and then I have to tell it where the Verilog source code is. But otherwise it's very straightforward to wrap existing Verilog modules. I just realized Tuco is sitting somewhere super cute, and I need to point the camera at him. Hey, Tuco. That's a good spot for a cat. A little behind on the chat, but yeah, I definitely recommend getting started with FPGAs if anyone has inklings to do so. They're, they're cheaper than ever. I think you can even find dev kits that are much cheaper. I mean, this is the Papilio Pro. This is like their fancy version because it has RAM on it. I mean, FPGAs typically have built-in RAM of, maybe 10 or 20 kilobytes usually on FPGAs this size. But if you want like a large amount of memory, then you'll have to have an external chip usually. And to get a large amount of memory at a reasonable price, you usually need DRAM, which you have to have some control logic for. So it's also nice that this has this has a pretty nice memory controller architecture. Actually, I haven't gone super deep into it, but there's like a way that you can build kind of a pluggable like SDRAM modules where you can specify the memory timings, and I mean, it seems like they've made it relatively easy to add support for new memory chips, basically. All right, so that's what I got here. Then I haven't been using that super much. Like if you instantiated this on its own, so this has no interface for actually, for a CPU to talk to. It has an interface that you could plug some external hardware into. So it really is just expecting these two signals. So a very minimal implementation. You could wire up these pins up to the actual SD card bus, and you could wire up these completion signals to just complete immediately when the activity signal goes high. So if you set read go equals read activity and write done equals write activity, then if you saw, some of you might have seen a tweet earlier that I sent out about, I was complaining, well, not really complaining, it was like tongue-in-cheek complaining because, like, of course, but I was saying that getting a CPU in the loop slowed down my I/O from like 20 megabytes a second to 20 kilobytes a second. So the 20 megabytes a second was when I was just attaching block read go to block read activity. So that would be even faster than if you had hardware filling the SRAM, since even that would take like 128 clock cycles. So yeah, unreasonably fast, but a decent way to test to see if this module is actually working. But aside from that, that's not super useful. So the next step I made was to subclass it yet again, or not really subclass it, but make like an add-on class here. So this SD emulator is something that sits on top of the link layer, and so this LL submodule is the link layer that we wrapped below. And then this sits on top and provides some just basic interfaces for connecting this to a CPU core. So unlike the stuff that Project Vault's ORP was doing, where they actually threw a ton of hardware at the problem to try to make something that was fast, in this case, I don't care about fast. I just want something that is small and straightforward because I'm just using this for experiments. So in that case, I'm just giving the CPU direct access to those two SRAM buffers, the ones that in Project Vault would be filled by that little hardware DMA master. And the CPU has read access to all these input signals where it can see like what block are we reading, is there like an erase in progress. And then the CPU just has sort of strobe outputs so that when it writes anything to this register, it signals the read's complete. When it writes anything to this register, it signals the write's complete. And that's just done by creating general purpose registers here that don't really have anything backing them, and just wiring up the completion signal strobe to this block read and block write completion signal. So yeah, this is my favorite part of MySock so far is this register system. Like literally I can just throw a signal anywhere I want and wire it up, and then I get code generated to read and write it from like either C or C++ or Rust. So that's pretty cool. Yeah, I haven't tried it yet, but it has code generation for Rust, and that might be a great excuse to start using Rust for something. So Oh yeah, I just saw a comment in chat that the Lattice Ice40 are nice because of the open tool chain that works and having make files that work without licensing, and I totally agree. If you're looking to get started with FPGAs, but you think you might be put off by having to fuss around with specific Linux distros and install 30 gigabytes of toolchain, then perhaps that's what you want. There are even like shell scripts. Somebody has a shell script on Git that you can run that just compiles everything for Mac OS and I think for Linux, and just, yeah, compile the whole FPGA toolchain from source from Git. So those are really nice. Yeah, definitely get one of those and check it out. They're like $20 for the iStick. They're pretty small as far as FPGAs go, but you should be able to fit a CPU and some basic stuff in there. It wasn't nearly big enough for this SD emulator, since the SD emulator is not super efficient. But I think it's the HX1K named because it has 1,000 logic slices or logic elements or whatever they call them. So, and those basically map to something that stores a bit and does computation on 4 inputs or so, if I remember right. So we've got registers, and then this is our bus interconnect. So like this replaces pages and pages and pages of Verilog vomit from the reference platform. So there's a Wishbone kind of adapter module that knows how to glue Wishbone devices to other Wishbone devices, and I can just create a bus that the system on chip knows how to glue stuff onto, and then that bus is backed by a decoder module, which is actually some hardware that lives in this module, and that decoder has the addressing logic to figure out which of these bus slaves are actually being addressed. And then it connects the appropriate SRAM instance here, which is something that takes the Wishbone bus and glues it onto the SRAM interface that MyGen knows about. So these are the actual memory buffers that we exposed earlier, right down here. So like that's all it takes to have memory mapped SRAM. So that was pretty fun. And this is all it took to add interrupts. So there's a small abstraction layer built on top of interrupts. There's like an event system where an event is just something that, I think it's just a slight generalization of interrupts, because you can use this for the same kind of signaling that you would need for an interrupt, even if it's not actually a processor interrupt. So I think it makes sense to name the modules a little bit more generically. But this is basically the functionality you would expect from an interrupt manager. You have subclasses that detect interrupts in different ways. So there's one that is latching, and then you have to explicitly, there's like a latching interrupt source that you have to explicitly clear. This one is just a level triggered interrupt, basically. So the interrupt happens, the interrupt will happen anytime these signals are high. So, and I want that so that I don't want to have like an interrupt state that can get out of sync with the actual SD emulator state. So I want the interrupt state to be just directly based on the state that the SD emulator hardware is already keeping track of. So in this case, I've just got 2 level trigger interrupts that are wired up directly to the kind of transaction active signals. And this seems to be a great match, because as soon as these go high, we'll start interrupting, and then when the CPU pokes at these completion registers down here, then the external SD emulator hardware will end up lowering these levels before the CPU gets a chance to evaluate them again. So that's everything. That's all it takes. There's really not much here. So that just gets wired up in this module and then compiled, and then we generate some headers. So all of those registers that we were seeing, we have some accessors now, so just functions we can call. And then I have some very simple software for this so far. So there's a main program, has very simple libraries for doing serial and using that one timer that we have compiled in. It's like one 64-bit cycle counter. So all this is doing is initializing modules and then periodically printing some status to the serial port. And all the real stuff is done in these other modules. So this is like the driver for the SD card emulator. So we have initialization, we're just turning on the interrupt source. And then when the interrupt happens, there's like a little bit of interrupt dispatch. Since there's only one interrupt vector in this processor, the way it's configured right now, we're just checking which interrupt actually happened and calling the right vector. And then in the actual interrupt vector routine, we can distinguish between reads and writes. And then we just service them by calling a software function that generates the proper buffer contents for a read or stores a buffer for a write. And then we signal to the hardware that we're done. And that's pretty much all there is. Like, this signaling is all we really have to do. This is just to generate some contents for the buffer. And then this is just bookkeeping so that we can periodically print out the status and see how many reads and writes we're doing. And that's because, for a number of reasons, we don't want to access the serial port in this interrupt handler. It could deadlock because of the way the interrupt priorities are set up, and it would be too slow. So we just want to print out serial status periodically in the main loop. So then this just needs some external functions that handle individual 512-byte block reads and writes. So that I've implemented over here. And this is, like, I think what maybe took the longest. I don't know. I think I spent like a lot of this week figuring out what tools to use and then learning those tools. And then I spent like a lot of yesterday learning enough about the structure of FAT16 to write this code. So this is basically kind of a really weird, I mean, it's kind of like the code you would write to format a file system with FAT, but instead of writing to a disk, it's serving blocks as they're requested. So the way this is implemented, every time the disk is read, you could take some kind of special action. So in my case, I want to potentially return different file names, and I want to set up a hardware trigger that I can use to deterministically trigger the scope after a particular block has been read. But you could do other things here too. So in this case, that block read from the other file, that switches off into different implementations depending on where on the disk we're reading. So we have a boot record, or master boot record here. We have the FAT boot sector. And so all of this is just, you know, all the legacy stuff that we need to tell the driver, to tell the file system like how big the file system is, and you know, where the clusters are and how many of them to expect, and where the root directory is located. And in this case, I've tried to keep it to a really straightforward FAT16 file system, with no bells and whistles. And then really this is the kind of center of it all. Once we get through all that, and we're reading directory entries, this is what actually gives file names to the, you know, to the device that's reading from us. So there's a special case file that actually labels the volume, but then after that, all the files are just text files that I make up the name for on the fly. So I think that's enough talk. Let's try demoing this. So that compile finished, and we can flash this to the board. And it's not plugged in. Let's plug it in. Okay, so still got the logic connected and the Papilio board. It takes a sec to program the Papilio. Okay, so right now we are using the FTDI chip via the FPGA to program this SPI flash with both the FPGA bitstream and the BIOS software, which is basically the bootloader and kind of monitor software that runs on the system on chip right after it boots. So those are both done. So now if I did this other build target make term, so you could watch it boot if I press reset. So my sock BIOS tells you it was built like just now. And here's all the initialization. And this doesn't have a whole lot of stuff to do, but we could read and write memory, and we could read and write registers. We could run a memory test. But I mostly want to not be using the BIOS and instead program the experiment software. So I have two experiments now. Or two pieces of software now. This needs some refactoring, but I've got this one directory that I'm turning into my experiment for flipping through file names. So it's got a file name guess here that I'm updating from the serial port. So I've got a handler for the WASD keys to step through the file name and change the guess. But I've also got this simpler file here that one just prints out status, and then the blocks here are, and this is the one we were looking at before that just makes a bunch of text files. This one makes all different files with different first clusters. And then the file contents, each file is 4 sectors of Ds with a label at the front. So if we install this firmware and reboot so that it can connect to the bootloader. Great, so now we see this loop. So this is running on the CPU we just compiled and printing this stuff through the UART we just compiled. So it's running this loop here. So now I am going to plug this. I guess I'll plug it into macOS. I'll take a closer look at what's going on soon, but right now I'm just going to plug this into the SD card reader. Cool, so you can see those read and write are counters, just saying how many blocks were involved. You can see macOS tries to write to the disk right after I plug it in, which is a little bit rude. It's some kind of desktop file or something it's trying to put on. I thought I could have it not do that by having the disk be full, but I think the disk, yeah, so I don't know what it's trying to write, but haven't looked into that yet. But anyway, the reads are the most important to us. So let's put this in a window. And let's see. So we should see a disk, flipsy. And we can see that it mounted successfully on macOS as a FAT16 disk. And there's the device name. Let's make this a little bigger. So we can list out the root directory. Got a bunch of those text files. I didn't bother setting the timestamp on any of them. You can also open this graphically. So you can see that the file system's caching the FAT, so we would have to provoke it to reread that somehow if we wanted that. But in this experiment, I'm going to be rebooting the target processor a lot, so that doesn't really matter. So you can start to see, if we open up these files, then we see 4 blocks here, each labeled as, this is the cluster number, and then each cluster is 4 blocks. So labeled 0 through 3. And that matches up with what we're generating over here. Oops. Yeah, FAT data block. So this is generating those file contents on the fly. So it's not very fast, but Let's make a little disk image so that we can take a closer look. That was disk 2. Let's just read the first megabyte. And all right, so here's our little disk image. Boot sector, padding. there's our boot, our fat boot block. That's being constructed by this code over here. You can see the fake DOS is our OEM name. And there's the file allocation table where I'm trying to say the whole disk is full. The other reason is in case anybody checks to see if a cluster is allocated before actually reading a file from it. They'll see that all the clusters are allocated. So I can just tell folks to read from wherever. And then here's the actual root directory. Volume name, and then all the files. And this is fixed size based on the way the fat is allocated. So in this particular arrangement that I've chosen, there are 512 root directory slots. And then we just start getting data clusters. So it'll just keep generating those data clusters. The sizes are totally arbitrary right now. I'm just basically copying sizes arbitrarily from whatever references I was using and trying to get this thing to look like a proper fat file system. So the SD card is still emulating, I think, a 128 megabyte card. And then the partition table I've set up as a 32 megabyte FAT16, since I had a 32 megabyte SD card that I could format to see what its fat looked like. So I copied some numbers from that. But that would be easy to change if anybody cares. It's just right now totally arbitrary. Let's see how fast this would read. So that first megabyte, oh, that must be cached. Let's try reading 10 megabytes. Oh, that's better than I thought. Yeah, I was seeing this running much slower before. I guess I must have either fixed something or it's being run in a different mode this time. That's cool. Can I do something later on? Oh. Seek. Oh, I didn't mean to make that larger. Oh. I must be using that wrong. Oh, right. Haha. Block size. Cool. So that was just reading from kind of right in the middle of the device at 2.7 megabytes a second. So that seems pretty good for having a CPU in the loop. The CPU, I think, is running at 80 megahertz right now. Oh, why are these blank? Well, these aren't blank. I don't know what this 0 region is for. Anyway, I'm not going to be too fussed about that. Let's take a look at the logic, because I want to get at least some footage of how it looks on there, but I think I need to switch over to the oscope soon, because the next thing I want to implement on this is a triggering system, and I really want to look at the timing there. So I've got my logic cranked up to 100 megasamples, which is not fast enough to reliably get the clock on this thing. I think the clock is around 50 megahertz. So right now I've got just the clock, the command serial bus, and this debug signal I think is wired to read activity, so this should go high when we're in the middle of a read. I think this is all I can get and still have 100 megasamples. So let's try that, and then just I'm going to unplug this card and plug it back in. Cool. And then if I start catting some files, we should see that collect some more data. Yep. Okay, there's our logic trace. So the initialization starts out pretty calm. So in the SD spec, there will be a bunch of these kind of resets. Actually, I expected to see more blank clock cycles. Usually there's a lot of empty clocks when it's first initializing the device, but oh yeah, I should find make sure to mention this plugin I'm using. So this is not a standard feature in Salia Logic. This is actually an open source SD protocol decoder, which has trouble keeping up once the card goes into higher speed modes, but is super handy still. Let me find the web page for that. Yeah. Whoa. How did I... That's like the first time I've accidentally used the force touch, and then it's actually been what I wanted. Usually I accidentally force touch on this laptop when I mean to be doing a drag. Okay, yeah. This is what I'm using right now. It's super handy. And it's not perfect. It doesn't quite decode as much as I would like, but it's way better than nothing. So, and you can see that the protocol is a little weird. Like there's a start bit, and then that's the command, and then there's a CRC. I think the CRC is like 6 bits, and then there's a stop bit. So it helps to have a decoder. It's a little bit more decoder worthy than SPI even. So this is initialization. These groups are actually command prefixes. So command 55 is like a modifier for the next command, so this is actually termed a command 48. SD is really weird. So that's like, I think this is just initialization and probing for the card's ID. And then way over here we actually maybe start to do some I/O. Oh man, this clock is too much to keep up with already. So yeah, so it's doing the initialization at, I think, only like 3 megahertz. Oh geez, 200 kilohertz. But like now I'm already having trouble resolving the clock with the Salia. Like I'm just getting, it says 50 megahertz, but then I start drifting out of phase, or like in phase with the clock, and then I just start losing it, so it's probably close to 50 megahertz. So yeah, this is about all the usefulness I can get out of this logic analyzer. As much as I like the decoder, I could turn off high speed mode, but I don't really need to. I think I'd rather just switch to the scope at this point. You can kind of see what's going on, even without the full decoding, that, here's some initialization-y kind of stuff, but then these are burst reads. So there'll be a command setting up the read, and then, or actually this might be like, what is command 63? That's not even right. Yeah, I don't know what these commands are, but like this is the actual burst read command. This would have been something that it wanted to issue before the burst read for some reason. And then so you can see this is reading this is reading 5 sectors. So each sector, this time that this is high is when we're waiting on the CPU. So 65 microseconds for the CPU to generate a block and then return it. And then here's the turnaround time for the hardware to actually send the block over the SD interface and then do the acknowledgement with the other end. So CPU is definitely the bottleneck, but unless we want to have the complexity of a caching scheme, this is probably a good trade-off. And the hosts will be happy to wait for this amount of time. I mean, it's normal for SD cards to have to do their own processing. I don't know what the spec says about maximum delays, but like the readers that I've tried seem pretty happy to wait for quite a while. Okay, let's get this hooked up to the fancy O-scope. And I think I want to do the triggering system with it still connected just to the laptop, but then the next step will be to move it over to the device under test that we actually care about, which I think I'll have to use jumper wires for that because I don't think this will mechanically fit in the SD card slot the way it's put up right now. Oh, Tuco has an even more cute spot. All right. Thank you, Celier. You've served me well, but are too slow for this job. Oops. That ended up unplugging more than I wanted to unplug. Let's put this back on. Clock, command, 4 data pins. I was reading through the relatively recently released SD card specs. It used to be you could only get the specs if you were like an official licensee, so all the non-official folks like me had to do things like, read the source code to open source projects and try to guess what the spec said. But sometime in the last several years, they released like a subset of the spec with all the parts anybody actually cares about, unless they're doing DRM, basically, and made that publicly available. So I was reading through that, and there's so much stuff in there, so much that I don't think people actually use. But yeah, I saw the specs for some new, even higher speed mode that uses a differential pair. Well, a couple of differential pairs that are behind the usual SD card pins. Crazy. Okay, let's put it this way. mix our signals today. Oh, now I'm imagining a bar called mixed signals, although I think that would be taken wrong. I mean, it would have to just be called mixed signal, and then people would just assume it's plural. I guess you could turn that into a pun and run with it, though. Okay. Let's break out, like, everything. So I think I want 0 through 8 to go to my debug port, just so that they match my debug numbering. And then I'll stick the SD card up here somewhere. I want these to be my data bus. Ground. These are really cute. I love all the little wiring accessories that come with this logic pod. These clips. They're designed to accommodate, I think, a range of pin sizes, but it means that sometimes they're a little tight on these square headers. I think that maybe they're just slightly wider than the spacing, so they crowd just a little bit. All right. And these all go to debug ports. So I think I'm going to be using this 8-bit debug port as a trigger port shortly. Like the way I imagine this trigger system working is, at first I need to determine where I want the trigger to happen. I don't think it would be sufficient to have it trigger on when that activity signal goes low on the external bus interface, since that's not actually when the SD card finishes its thing. That's just when it's allowed to start writing the block back that the CPU's finished writing. So I think what I want is to have some registers where the CPU can write a trigger value, and then there's like a delayed latch so that shows up on this port, like these outputs eventually. But, so basically be like a register that gets copied to the GPIOs when the next SD card command completes, for whatever value of complete seems most relevant. Because what I ultimately care about is when the actual processor reading this file system gets to the point of starting to process a block. So closest to the actual end of it on the wire as possible. All right. Oh, there's a good suggestion in the chat to do like a roundup video on this. I definitely do those. They just usually take a while, and the streams are kind of my way of sharing stuff in progress, even when it would take some time to actually get the final videos out for stuff like this. All right, let's just get all this up on the scope. Is there a way to reset all of these? There we go. All right. D10, huh? This looks like it's getting stuck. Maybe I'm not running the firmware. Maybe it's just in the BIOS. Because this looks like the SD card is timing out, waiting for a completion. Oh, did the serial port come disconnected from the VM? Here, let's get this scope back up on this screen, actually. I think that's what I need. That cat looks peaceful. All right. Connect Flipsy. I think VMware still cached the name, so it still thinks it's Flipsy, even though it's currently not responding to read requests. That's pretty cool. I like how I can just upload the firmware to the SoC, and I don't even have to plug in the SD card. I can just have it continue its IOs. So yeah, it's already read the root directory, but you can see it kind of works in spurts. It's interesting. Okay, let's try triggering on these read transactions. So D3, I think, or no, D0. What's going on? Not triggering. Oh. Yeah. Great. That's a much clearer view. So now we're actually seeing the reads basically from the perspective of the CPU. So that trace D0 at the bottom is high when we're waiting on the CPU, and then the little spikes above it, D1, are the completion pulses that indicate the CPU just finished. Don't know why we're seeing D2. I think D2 is supposed to be a write-related signal, so I don't know why we're seeing anything on D2 right now. That might be a bug. I don't think writes are working, well, I mean, writes are intended to not be implemented, but I don't even think they're necessarily stubbed out correctly right now, but I haven't been too fussed about that just yet. How fast is this clock even going? Yeah, it's like right at 50 megahertz. So those are our two clocks. We have an 80 megahertz CPU clock and a 50 megahertz high-speed SD clock, which also sometimes runs much, much slower. Let's get some more traffic. What disk node is this? Disk 2. There. All right, we've generated some more traffic. I'm confused by D2. D2 is bothering me a little bit. So that is supposed to be, I think, the right activity signal. That would be up here in the target where I'm setting up debugging. Oh, right here. Block right active. I mean, it is a combinatorial signal. Maybe it's glitching. Or maybe it's bad grounding. Let's put another ground wire on and see if that helps. Maybe a couple more. Oh, did that fix it already? Better grounding to the rescue. Yeah, I think that edge was due to bad ground. Let me put one more on here just for the hell of it. All right. Much cleaner. So curious how wide that pulse is. Oh, that's like 10 nanoseconds. Yeah, 13 nanoseconds. Neat. There's one CPU clock cycle. Okay, I'm no longer concerned about my debug signals. That was just an electrical issue. So then, what did I put on D9 and 10? D9 is debugging, but 10 is the clock signal. Maybe I'm not driving D9. I probably shouldn't worry too much about the glitches. I don't like anomalies on my bus. That's probably bad grounding. Do I have any more of these little ground wires? Oh man, I'm using up like all the grounds on this little breakout I made. Always need more grounds than I expect. Did that fix it? We're no longer triggering on D9. Yep. Yay. Oh, okay, that's much cleaner. So D0 and D1 are indicating our read cycle. Then the top 6 signals are all the SD card port. So D10 is the clock signal that just kind of turns on whenever it's busy. Then D11 is the command bus. And then the other 4 are the data bus. Persistence on. So if I trigger on the very beginning of a read cycle, you can see its relationship to the SD card command here. It looks pretty stable. But I guess we're getting a few different kinds of reads here. Let's trigger on the completion again. Can we generate more consistent traffic? 5 12-byte blocks, maybe? That low spot in D0 pretty much perfectly matches the time we're actually transmitting data. So I think if I look in the phi, there's probably going to be some signal to indicate the end of one of these data packets. I don't like how much this is jumping around though. I don't know where that's coming from. It might just be I mean, it might just be the clock domain difference, but it's weird. And that's another reason to have a trigger that's generated by the SD, like phi state machine, because I really want it to be on the SD card's clock domain. This is just messy. Those glitches on D11. That might, I might see glitches on the bidirectional lines when they turn around between the two devices. Oh, you know, there's probably maybe I should start by looking at how it controls when it's writing to the tri-state lines. Oh, there's a good question in chat. It's interesting that D13 is much busier than 14 and 15. I think that's the pattern that I'm writing. Because what you're seeing, like this block is a bunch of repeating bytes. So I think what you're seeing is that a lot of the bits are the same between the top and bottom nibbles, but that bit was different between the top and bottom. Actually, I can make a better test pattern if we want. Where am I? Simple block layer. And that was, so this is, most of the disk is going to be these data blocks. So if instead of D, I make that something like 0x5a, now these two nibbles are mirror images of each other. So if I run this, we should see a lot more activity. I might need to restart this. Yeah, if it errors out, I kind of need to replug the device. Come on. It's sometimes so slow to open or to mount. Disk 2 S1. There we go. Yeah, that's about right. Yeah. So you can see how bad it would be if we tried to use this as a trigger signal. This isn't really lined up with the SD card at all. We really want a trigger signal that's lined up with the SD card somehow. So let's get that. Let's get ourselves a little bit more screen space. Wake up. Okay, so software. Let's take a look at the hardware and see where we want to add this thing. Well, so actually, to be clear, I don't really think we'll need to modify any of the existing code. I think that this can just be kind of a bolt-on module, which should be nice. I want this SD card emulator without the triggering to still be a useful thing on its own. So I'm interested here in, so this is the signal that tells the tri-state buffer when it should avoid writing any, when it should avoid driving the data bus. So looks like that's controlled both by this output enable and by card state. I think this is something much larger granularity, where does card state come from? Who decides what state the card is in? I don't think this is what we want, but I'm curious. Oh, that's coming through a synchronizer. On the SD clock domain. That is an input from the PHY, or from the link layer. They use these synchronizers anytime they cross clock domains. Okay, so there's a bunch of that. How do we enter disconnect state? PRG? Well, I'm not familiar with this part of the SD card spec. I don't think that's something that is common though, so I don't think we need to worry about that. Let's just look at that output enable in the PHY. Yeah, command OE, that's a register. Command OE. O state. I think that's actually already put out as a debug signal. Jeez, exact 5 cycle. Yeah. That would be hard to do in software. Yeah, response right end. Oh, response done. Maybe that's the signal we want. I mean, I don't think we want the response done, though. I think we want, like, the data block being done. Like, I don't, as tempting as the command state machine is, I think we want to mostly just focus on the data state machine. I think we mostly just want to use this state signal, but it'd be nice if there was something slightly more general. Like, I just want this, I think I want it to latch when it finishes. Oh, is this one state machine for read and write? Oh, that's just for write. That's just for writing. I mean, I guess there's my urge to make this thing super general, but I think all I care about are triggers based on reads. So maybe I just make this based on the output enable. Does this get deasserted between packets at all? I mean, there's this reset and idle state. Does reset go to idle? Yeah. Yeah, so that's when we're going idle. That's right after the stop bit, which is also a nice, like, the state would be useful as a trigger also. But yeah, I think all we need to do is make a latched GPIO output that transfers whatever value we just wrote to the actual GPIO when this signal goes low in the SD card's clock domain. I think that's what we want. So I'm curious, I think I will need to know how MyGen's clock domain crossing works, because now I care about that. I thought there might be some way for the registers to help out with clock domain crossings. Because, I'm imagining the block diagram of this thing, and there will be a little chunk of hardware that's just looking at the SD card output enable, and that piece of hardware is also clocked by the SD card clock, and that'll just be looking for the first SD card clock edge in which that's no longer asserted. And that'll be the trigger to move the data to the actual output latch. So the output latch itself will be clocked by the SD card, but the value it's getting comes from a register that's on the CPU's clock domain. So it's not a difficult clock domain crossing problem. Like, it would be just a matter of having a synchronizer. So this is maybe a bit of a tangent, but if you're not familiar with clock domain crossings, one of the issues you can have is that if you have this one clock that's controlling some circuitry that's expecting data to be available at a particular time, and then it latches that data, and then it moves on to the next clock cycle. When the data arrives at kind of an indeterminate time, so like when it's latching, there's a moment kind of right on that edge where you could actually put the flip-flop into an indeterminate state. So it's not 1 or 0, it's just stuck and drawing more power than it should. And that's a latch-up condition. And you can make those significantly less likely by adding multiple stages of flip-flops when you cross clock domains. And so I think they're using like 3 stages of synchronization for this. But yeah, I mean, I could do that myself, or if there's a thing that already makes that easy, I could use that. Clock domain crossing. Oh yeah, how does this work in the Ethernet adapter? They use a RAM, or at least a FIFO of some sort, to clock domain cross. Oh, and there's a way to instantiate a submodule and then have it be in a different clock domain. That's nice. Anyway. Async FIFO. I think this is all in my gen land instead of in the SOC. Oh, this is, I think, what I was looking for. Clock domain crossing module. Multi-reg. Oh, yeah. I think this is a register. Yeah, so there's a bunch of nice clock domain crossing modules. This is great. Maybe this is what I want. Don't know that I necessarily need that, but... I think this is more of a timing guarantee than I actually care about, since like the timing involved in getting the register into the input of that output latch is not super critical, but the output latch itself is. I think this might be perfect. I think this is just a register that... I don't know where the actual synchronizer is. Oh, multi-reg implementation. Yeah, okay. And I can even just tell this what output clock domain to use. This is genlib cdc. Okay, let's make a new module for this. Need more terminal. Okay, so there's the SD emulator core. Let's make a new core for SD trigger. So let's grab some of these imports that we want. I don't think we need that or that. Genlib.cdc. I think we just want the multi-reg. All right, and then the actual core is going to look a lot like this. It's going to be a module with the auto CSR status registers. But let's just use this as a starting point. I'm not going to need much of that though. So this is going to be I know that color scheme is a little weird. I don't know who thought gray on gray was great for comments. It's like kind of nice. It's a general color scheme, but not necessarily the best readability. Oh, now I like kind of don't want to change it for consistency breaking sake though. I'm not going to worry too much about it. So then it's going to want access to the SD. I think I want this to have access to the link layer. So, and that's, I'm going to use the same naming there, but it's not a submodule of this, I'm just referencing it, so it's not going to actually show up in the submodules of this class. So I want, just realizing I didn't think I called init on the other module, but it still worked. I guess is that actually right? I'm wondering if they intentionally they made the constructors optional, or if I've just been forgetting that. Let's check some references over here. Yeah, I guess the constructor there is not especially necessary, because all of these similar classes from inside my sock are doing it the same way. So SD link layer, no keyword args, great. And I think I just want like one register. I'm already thinking ahead to if I want triggers on multiple different stages in the SD transaction. Like I'll need multiple registers and a way of keeping track of which ones are pending. I don't think I care though. I think I just want, I'm just going to call this latch, be very straightforward about it. And this will be a control and status register with storage, and then number of signals, which will default to 1. So that's enough to create a register that the CPU can, write stuff to. And then we need to synchronize it into the SD clock domain. So we need to borrow the clock domain from, I think there are multiple ways of doing this, but I think I can just copy the clock domain from that object. So there's, yeah, CD, SD, and MySock has this pattern where there are several of these kind of special objects that you can assign to within a module. So if I say self.clockdomain dot CD SD, then that'll also be available as self.cdsd, but it'll be registered as a clock domain. So I just want to copy the SD clock domain from the SD link layer and make it my SD clock domain also. And then I want so I'm going to name that SD clock domain latch to indicate that that's like my synchronizer for it. And this will be one of those clock domain crossing multi-regs. Not that. Oh, it's not in this one. It's in, well, whatever. I remember what it is. Oh, I kind of wanted to look up what that output is named, though. Mygen. Clock domain crossing. It's just called O. I, O, and O domain. Why are we taking a signal O as input, though? Let's see if we can find an example of how to use this. FIFO uses it. Oh, okay. I guess I was kind of expecting that it would generate its own signal and then I could just refer to the signal as a member, but it's expecting the signal to exist separately, which is fine. So that'll be the synchronized version of the latch, and then is that what it's called? I also need to look up what the name of the register in the CSR is called. So that storage register gives you a signal called storage. Great. So the input is the latch storage, the output is SDCD latch. Oh yeah, this can be an anonymous special. So it still needs to keep track of that as a sub thing that it emits when it generates the chip, but I don't need to give it a name. And I think this is going to be the output clock domain. Yeah. Oh, and you can tell the number of sinks too. Great. I think I want 3 just to match what the SD core was using. Yeah. Just making sure I can follow how this works. I think this is an array of all the different intermediate signals that it steps it through in order to do the synchronization. Oh, I see. And then the source is how it links them all together. Yep, neat. So that's great. Yeah, so just wanted to label those a little better. So that's the output clock domain and the number of synchronization steps. So now I have the register value writable from software in the right clock domain. Now I just need to actually latch it. So this is when I want to have a little detector for the output enable going low. So I think we can just pilfer the signal from the link layer. Yeah. So I can go into this TS triple and find just the output enable signal. So like basically like that. And this is being driven through an inverter by the code down there. And I'm looking for falling edges on that. So I just want to store the current and previous versions of this. I think this might need to be... This is something where I don't want this logic to be running off the main clock. I want this to be on this other clock. So maybe it makes more sense to put this in some kind of submodule or to use an existing submodule. Let me look for inspiration. I think I can take some more hints from how this FIFO is implemented. Oh yeah, and where's this gray counter? That's just another clock domain crossing thing. Yeah, I think I just want this to be a submodule. I think actually also this is going to need a bunch of output pins, and that will infer the width. So I don't need to specify that separately. And maybe not even that, maybe... So those will both match that length, and then I need that clock domain renamer. Where does that come from? Decorators. Oops. Do I not have copy and paste? I kind of have copy and paste. I think I want something like that. Just an instance of that in my special clock domain. And I want to give it my pins. And so this will just hang out driving those pins. And how does this fit on a line? I guess it can just be long. That's fine. I just have a big font here, so everything looks huge. So I want to give that the pins to output, and it also needs a latch in its own clock domain. And then it needs the output enable signal. Let's do that. So, latch specials. I don't think that needs to be externally accessible at all. Let's just do this. Fewer circular references and stuff. Okay, so this is the CPU accessible register. This is a copy of the clock domain. This is converting the register to the clock domain we want it in. And then this is instantiating the output driver. So cool. So all of this is, all of this is in the same clock domain. So we've got this that we converted, we've got the pins, we've got this output enable. That doesn't need to be split. Okay. So now up here in this module, this will be like a little utility that handles just the output side. So this needs the pins, this needs the latch in, and it needs the I haven't decided what naming convention. I think I'm going to use the one that the automated Verilog adapter uses and use a prefix like that. I think maybe let me just invert this to make this positive edge driven. So I'm just going to have this look for, can this just be a latch? Is there not just like a latch primitive? Because this is going to be very straightforward. There's probably a way to do this without having a separate module that I'm just not aware of. whatever. Let's keep this application specific. Fine. Let's avoid overthinking that too extensively. So then this will have some synchronous logic. This will need... I think this can just... I need to look up how this if works. I haven't actually used that yet in my gen. It's structure. Conditionals. I guess if is a statement. I thought it was an expression, but... Okay, so that needs to go... Okay, so we're buffering the OE signal so that we have both the previous and the current versions. And then if, oh, is this legal to have a, I have no else? Yeah. The else and elif are separate add-ons. That's cute. Okay. So then I think we just need to do if, and so we're looking for the negative edge here, so if OE previous, we're using bitwise operators here because everything's a bit. So like that's our condition. Then I think we just want, it's very straightforward. There's probably a way to do this without making it a separate module. I just don't know how to do that without, or given that it's in a separate clock domain. Let's see if that compiles. It does. Well, the Python part compiles and runs at least. And so now it's generating the FPGA for this. Oh, actually, I never called this, which might be why it's working. Let's actually make an instance of this. So SD trigger, self, link layer, and pins. So let's go back to our board-specific file. So I want to separate this out so that there's, I want to use some of these pins that had been labeled debug as trigger outputs. Make that an 8-bit port, make this a 2-bit port. And now, so for the debug, I'm just going to show these activity signals. And then here's the trigger. And let's actually import that too. Okay, so now it needs access to the link layer and some I/O pins. So that part doesn't need to be there. SDMU.ll, and then we can ask the platform for those trigger pins we defined up there. I think that's enough to instantiate it. Good, now we got some syntax errors. Line 22. Oh, is this defaulting to tabs? Why? I don't think I have this VM set to just make everything spaces like I usually do. SD trigger has no clock domain. Oh, clock domains. That should be plural. No. Oh, and that's a local variable. And this is also a local variable. Oh. Unresolved clock domain. Oh, maybe I'm not using this clock domain renamer right. Let's see if that's the problem. Can I get away without this? Guess this is not finding the clock domain either. Is there something else I need to do to register a clock domain? It might be that I have to make a new object here and then drive it from the other clock domain. That's weird. Well, let's see if that gets us there. It might not be the cleanest way to do it. So we're making a new clock domain called SD in this module, and then driving it from the clock domain of the same name in the link layer. I keep accidentally hitting that key. The key combinations are different inside the VM versus outside the VM. I remember having this problem before. How did I fix that problem? Oh, right. This is not the same problem. This is just the difference between a clock domain and a clock signal. Ooh, that's a good sign. Okay, I have a feeling there's a much better way of doing this module, but I don't currently know it, and this is probably fine. Let's see what this looks like in the generated code. So our registers. SD trigger. I should have an SD trig submodule. Oh, I didn't generate registers because I need to add this. Stop building. I need to register this as a thing that has CSR registers. That's why I wasn't getting any registers. So now we should see that. Yes, SD trig. SD trig latch right. So we should just be able to do that, and then I guess it's our how do I want to manage clearing? I guess I assumed that I would just write a 0 value when it wasn't a packet that I'm interested in, so that it's always latched when a write completes. I think that's the simple value, or a simple way to start doing this. So, for example, I could go into the or let's go to the simple software. Well, I'll go to the experiment. That makes more sense. So, I think I want to set the trigger at the bottom of this block read function. I mean, I guess it doesn't really matter where I set it in here, so I could just set it directly. Let's have a default here. SD trig. So let's clear this if it's an unknown block, or I guess that's why I wanted it up here, is I don't want to have to do this in every single switch case. No. Okay, so we're updating. On read completion. And let's start setting some bits here. So root directory entries. Let's just use something like that. Okay, this is still compiling the gates, but I think we can just, on a separate terminal, compile the software and see if it works. Oh yeah, I did just call it triggers. So this will just be a little byte we can latch down here. Yay. So that's not going to do anything especially interesting until after this hardware loads. Maybe this is a good time to refresh my T and adjust the cat camera. I know the hardware just finished compiling, but I think I really want to make this output pulses and like automatically clear the trigger. Let's test this though. Also the cat. Because I think I would really like to be able to give like just a trigger on every block. And like that, and then like that. But then I want it to go low after, a small number of clock cycles so that I can use it as a trigger regardless of what else is happening. So in that case, I actually want this to be a counter. That's fine. SD trig. SD trig latch right. Why is that an undefined symbol? Is this building against an old version of the libraries or something? Okay, I guess I needed that file. Well, okay, maybe I won't test it. Maybe I'll just make it better and then test it. So I want some control over how long these pulses are. So what kind of counter primitives are hanging out here? So let's make a parameter for how many cycles the pulse should be long. I'm just gonna say like 100 for a default. That's probably too long. Maybe 10. 20, sure. And I think I want to do the same, log2 int trick. I think the true there is about whether or not it has to be a power of 2. Need power 2, gotcha. So that should be... So we want a counter that's big enough to hold that, but doesn't have to be a power of 2. And then let's have that's what I want. So I'm always saving the previous output enable so that I can check for these edges. If I detect an edge, then I reset the counter to the number of pulse cycles, and I immediately latch the trigger outputs that were provided. Then I count down, and when the counter expires, I latch 0 onto the trigger outputs. I think that's what I want to do. See if that works. Commas. Compiling the BIOS again. Okay. Oh, interesting. There's a pointer from chat that there's some audio interference between the audio and the video. I'll have to look for that. I wouldn't be surprised if there's a ground loop creeping in there somewhere. Oh, yeah. I think I know what that's from. Ah, I was wrong. Wireless headset. Must have must have that wire near something. I'll have to check that out. So while this is compiling, we can take a quick look at the generated output we have here. Software. Okay, so there's our SD trigger. The FPGA design ends up mostly one big Verilog file. This is the output of my gen. It's actually fairly readable as far as this stuff goes. It manages to name all the signals pretty well, and remove as much redundancy as it can. A lot of wires. And so this isn't going to be the CPU core itself, because the CPU core is an external Verilog module, and it isn't going to be the actual SD emulator, but everything else in the design is just this one big Verilog module. It's actually not even that big. So there's just a lot of glue for connecting stuff together. So register reads and writes, and whatever this is. A lot of this is connecting buses. And the UART. SDRAM controller, SPI flash peripheral. And here's the instance of the CPU here. I/O. Here's the actual PLL. This is what multiplies the clock up to 80 megahertz. Yeah, I don't remember much about myHDL. It's another Python-based HDL. I remember trying it a little bit, but so I couldn't really tell you that much about the differences between myHDL and mygen, but I really like this. It seems like it's not just the HDL, but a lot of the ecosystem around it that you would need to make it really useful, like all the FPGA vendor-specific build stuff, and Wishbone bus interfacing, and it's pretty nice. Oh, I think it's ready to flash. I'm still getting this error. Maybe I am blind and... Oh, or... Maybe I just didn't include the header that I need to in this file. Yes, that would be it. You win. So... generated /csr.h. Oh, that's better. So now I'm waiting for the bootloader. Yay. Okay, I think we need the O-scope again, thankfully. Okay, so I should see at least that low bit of the trigger happening on every block read. Oh, let's have this VM be less full screen. That password again. Ooh. I think we have a trigger. How good is it? It seems like the length is sometimes twice as long. So that should be trigger number 5, or 101, whatever. Cool, so that's the file cluster, which is what we would expect from just reading like the whole disk. Still not looking stable though, so something is happening that gives us like twice the trigger, which is weird. And this is not actually the end of a packet, so I think this is not triggering at the right place. Or, maybe it is. Oh, those could be different because of different SD card clock speeds. Those all look pretty consistent. Yeah, and then that's in a higher speed mode. Okay. That is not a bug. That is basically the way it's supposed to work. I mean, I could choose to time those using the other clock, but there wouldn't be any reason for it. Like, that wouldn't make them more consistent. Let's see if we can get, well, I guess I am already trying to read these one block at a time, but I'm sure the file system layer is caching it. Oh, let's try rdisk. Does that help? Oh, it does. Thanks, lack of file system caching. That is pretty baller. You can see the stuff jittering around a bunch. That's the moment where it starts and stops the SD card clock. That's changing relative to when the transaction actually finishes, but the completion is dead on. Oh, now it's using high-speed mode again. Stop being smart. What if I use a block size of 1? No, you just can't do that. 512 works though. Oh, cool, there's the data that's being generated. So you know how we had those packets that were like mostly Ds, I guess, and then, because we changed it to FA, but I think that was on the other source tree. So that's like all the D characters, and then the little printf region near the end. And some glitches on the command line. That's pretty nice. Okay, well, let's check this in, and I think maybe the next step is to just plug this into the PLC and see if we can get some side channel analysis going on. So what did we actually have to change to make that work? So we've got a new file. So we added some code to actually set the triggers in the experiment. Oh, let's revert this, because I don't really want to do that. And then SD trigger, change some IOs around, and wire it up. That's all it needs. Good old hardware. I think that one's not an important password, but whatever. Might as well be paranoid. Okay, so we've still got our reads happening in the background. Oh, while we have the scope out, I thought it might be fun to try plugging this into the built-in SD card slot on the laptop, just to try a different host device. This needs a adapter from micro SD to full size. Ooh, I don't know if I can fit this in there with the HDMI. It just sticks out a bunch. Well, maybe we lose monitor momentarily. Seems to be working. I've sometimes had trouble with it on the built-in slot, but I think that's because I was doing confusing things and macOS kind of gave up talking to me after a while. Also might be trying to use some mode that's too fast for me. I'm not seeing it on this computer currently. Oh, maybe I am. It was showing up in disk utility, but it was like grayed out, which is weird. I don't know if I've ever seen it do that before. Yeah, I think I'm confusing the SD card reader. also could be that this adapter does not fit super well with this tiny micro SD thing. I mean, I am getting packets through, obviously. Something about the OS still. Oh, there it is. Now it's grayed out again. Why is it grayed out? Can I DDE stuff from it? Disk 2? Oh yeah, there's... I don't know why Finder is showing it grayed out. It works fine as far as DDing blocks off of it. It could be I've got some small problem which is causing it to not read the file system properly. That's an interesting data point. There might still be a bug lurking in this that I haven't dealt with, but it's probably enough still that I should just plug it into the PLC and see what it can do. Oh, yeah, good point in chat that if I want to be really paranoid, I shouldn't type passwords while the sound isn't muted. That's a good point, but I mean, there's already multiple layers of paranoia here. I wouldn't use like an actually important password while I'm streaming. Okay, well, anyway, enough of that. So, back to this thing. Oh, Tuco, what a good cat. Okay, so, oh geez, what a mess. I think I just want to make another cable similar to this one, and, or even just like untape it from here. I kind of want to keep that taped on though, because it's convenient. Seven wires. There's 7. That's right. Might be easiest to just buzz this out with the multimeter. So this PLC has kind of a weird little drawer that holds its SD cards. Is this too close to focus? Nope. So yeah, this just kind of plugs into the board like that. I had already added another header up here to kind of break things out further. Yeah, a little bit of super glue residue on this card still. Okay, so this is unplugged. I'm just using this as an electrical reference. Fine, maybe I will use these wires just to have the color scheme be consistent. I think it'll be easy just to transfer these. This is not mechanically very solid. Okay. Command. This is clock next. Clock. So many pins. Actually, I'm still used to so many things being parallel, like when I was learning this. But it still, in some ways, seems like it's novel for so many buses to have so few pins. Clock, ground. Data. Okay. I think that's right. Let's see if it works. Oh yeah, this thing needs power and clock externally. This needs a few things actually. It needs Ethernet. It needs USB 5-volt power for the Raspberry Pi. It needs USB for the clock generator and the FPGA. And this needs power. Volts. Don't like having uninsulated 12-volt wires hanging out next to all this logic. Let's put some tape on that positive 12. And one more power cable. Power cable. Somewhere I had another power cable. Oh, on the chair. banana plug bus bar for these things. Alright, and that powers the... Oh man, where does that come from? Oh, that's the reset signal. Right, I have this set up slightly weirdly. And... okay, I still need clock. So this is the Mac Mini, which will run the Chip Whisperer. Oops. Not right now. Alright, so now I'm just setting up a clock. Not really using any of the Chip Whisperer features for this, I'm just using it as a clock generator since that's what I have connected. And I need the other FPGA, the clock generator I have on the ICE 40. Okay, clock is now running, so that should be distributed to the two microcontrollers here. And oh, I don't need any of these probes in place. These were just for an Ethernet experiment I was doing earlier. Man, streaming makes me hungry. I'm gonna need a sandwich at some point. What is this? That's the Ethernet trigger. Unconnected wires always make me frustrated with this thing. So, power. I think we should start to see the semi-bricked device at least updating its LCD a little bit. Yeah, okay. I don't know if you can see that, but the LCD powers on when I hit reset, and sometimes it draws garbage to the LCD. Okay, so now I should be able to, again, probably with the power off, plug the emulator in, and we should see if it's actually starting to talk to this thing. Let's see the scope triggering. Oh. It's talking though. Alright, I think the way I was usually proceeding at this point was to actually generate a periodic reset signal via this little BNC. So I'm going to have the scope go back to doing that. up a pulse. Pulse width, 1 millisecond, period, 2,000, yeah. Just have it be 2 seconds. Resets for 3.3. All right, so that should reset this thing. And let's just have the scope trigger on that reset signal. Now I plug this in. Okay, so that's like 20 milliseconds after my trigger here. Oh, I should trigger on the end of the reset pulse. I guess I can't. That's fine. I think this might just be the CPU coming out of reset. Oh, maybe that is something else. That just looks like noise. That looks like not noise. The other problem I was having with this experiment using a real SD card was that the initialization time was not deterministic. So I would run this experiment and reset it, and it would be somewhat stable, but you could tell that it was... So like, I mean, this amount of instability, I think, is just caused by the kind of analog parts of the reset cycle. So like the actual time it takes for the reset pin to rise up slowly, and then the time it takes for the oscillator to start. But what's that? But what I was seeing with the other SD card is the initialization was started around the same time, but then it would end up polling to see if the card was ready, and the number of polling cycles would just change dramatically for no good reason. So my first impression is that maybe what's going on is it's sending an unsupported command or something along those lines, and it's getting stuck in a loop because it doesn't look like we're actually completing anything. But I don't know, that is data. Or I mean, it's like stuff that's data shaped at least. So you can see these little bursts of 8 clocks at a time during a knit. And I've got some commands. I think that data line is just not being driven by anybody right now. So I think these are the actual commands coming through. Well, maybe we'll need to go back to the Salier and decode this. Either that or just put some more debugging into the logic. well, let's see, get the Salia at least on the SD clock and command and see if it can make sense of that. As I cannot decode SD by hand in a reasonable amount of time. Oh. The FPGA is not plugged in to power. I thought I still had it plugged into this USB hub, but it's totally not plugged in. So this is just what happens when the card detect signal is there, but it's not responding. Wow, it does try again and keep trying. Wow. Okay, let's try with power this time. Let's get our HDMI back too. I miss HDMI. And yay, dumb mistake for the session. Okay. Make experiment. All right. Well, I'm not seeing any read completions just here on the console. Well, that doesn't necessarily mean it isn't working. Still seems like it's getting stuck, but now it's getting further at least. Well, let's still connect the Salia and get this decoded. So, just need 3 wires for this. I'm like out of grounds. Guess I'm gonna have to use a clip for the grounds. Oh, there are so many other things to the sandwiches, though. I could have a burrito. Burritos are awesome. We have good burritos here. Yeah, I could have a burrito. Man, so many options. Burritos and micro grabbers. I feel like we're really close to being able to see some actual side channel analysis based on the file name. Like, we've come so far, I can't stop now just for a sandwich. But I probably can. I probably have to, actually, at some point. Not right away, but someday a sandwich may become necessary. And continuity will have to be sacrificed for the greater sandwich. These are just literally the first 2 signals. Clock and command bus. Alright. Salia. Alright, so... Whoa. want that debug signal. Just clock and command. As fast as you can grab them. Thanks. Got a nice little spurt of activity on every reset. Well, I'm going to assume this is when it comes out of reset. Yeah. So this looks like what I would expect for initializing an SD card. So it's starting out with a bunch of 0 clocks just to clear out anything from the buffer. And then this command 0 is a reset. This definitely doesn't look as clean as the waveforms you get from the dedicated SD card reader. It's setting it to 0 in between bytes, which is a little strange, but allowed. So reset, then some more commands. Not going to bother looking up what these are just yet. We've got a command 1. Is that where it's getting stuck? Command 1. Does look like it's getting a bunch of command 1s. Well, let's find out what command 1 is. Actually, I need to take a quick restroom detour, but I'll be right back, and then we can peruse the SD card spec. You're the star. Slightly out of frame now. Command 1. Alright. Let's find that spec. I think I have a local copy of it somewhere, but... Oh, yeah, I have it right here on my desktop. So, here's what we're looking for. SD specifications. This is the simplified spec. Oh man, this is new. This was only last year. So, and I don't know why it says confidential. This is like on their website. Anyway, I think we just want to skip right to the command reference. Oh, there is no actual table of contents. Command 1, mandatory. Reserved. Really? This isn't switching to SPI, is it? It's, yeah, maybe I'm reading this command wrong. Oh, so just to recap for anybody who just joined, so the overall experiment here is I have a fake SD card implemented on an FPGA, which I'm trying to use to suss out interesting file names that a bootloader is potentially looking for. But right now I'm just trying to get this to the point where it's actually reading the file allocation table so I can actually run the experiment. And it's getting stuck fairly early on during initialization of the card. Oh yeah, maybe that is a command, so there's this prefix, and then it doesn't resend the prefix when it resends the command. That might be a bug in their firmware, but let's see what this command is actually for. So this is a prefix, and then it's a command one, which also says reserved. Terminate video speed class recording. Maybe it just expects a different response to commands that aren't implemented. Like, I guess I could look at what this is seeing on a regular SD card. That would actually be pretty quick. Let's try, let's see, let's unplug this from the FPGA, and then plug in an SD card. And then run this until it resets a couple of times. Okay, so now I'm talking to... This looks a lot like the same thing, doesn't it? This is a regular SD card, isn't it? I mean, I know... Maybe I'm just resetting it too fast. Let's try resetting slower. But I thought I saw it reading the file allocation table way before it gets to this point. It's also possible I've got some kind of electrical problem that's interfering. You might want to look at some of these signals on the oscope too, not just the logic analyzer. Well, it does stop eventually. So that's... Maybe the stop is just from the reset. This looks like nobody's driving command. Maybe my SD card is not making good contact. It's also just weird that these are so back-to-back. Like, it's not waiting for anything, it's just sending a bunch of command one. What is even going on here? Let's try a couple insert removals. just get a different SD card that's not covered in glue residue. This one's 1 gigabyte. Getting anything there, scope? Oh, I unplugged power. Ha! Yes, always be having the power connected. Except when you don't want it connected. Train. Is this any better? This seems like it isn't retrying so much, which is probably a good sign. Okay, so the command bus is floating for all this time, which is a little weird, but whatever. And this is actually what we care about. And I don't see command 1 here yet. This looks like a more typical SD initialization. And then 0, 8, A command 41, A command 41, command 58. And then command 17 is a read. Okay, so this is just some electrical flakiness. This is, command 1 is not an actual command that we're getting. So let's save this trace and try to do this with the FPGA. So SD card out, FPGA in. Let's make sure the FPGA is running good firmware. So you can kind of see, so there is my file name guess. This firmware is just filling the whole file allocation table with a bunch of copies of that so that we can hopefully see a bunch of replicated string compares change. And then I can, step sideways and change only the suffix. This is behaving differently. Is it possible I just wired this wrong? Well, I mean, the wiring between the Salia analyzer and the SD card slot has not changed, so that shouldn't be an issue. I was using the same wiring exactly for the real SD card. Command 0, command 8. So maybe these are real, but it's doing this in because of some response that we sent. I don't know why it would be sending a command 2. Unless this is just, like maybe this isn't actually supposed to be 2. Oh yeah, there's some framing going on. What is this? So we got 0, 8, and then 2 over here. And then 0855 over here. That all looks fine, actually, with the real SD card, at least as far as I understand the protocol. Then over here, that's the same. These, is this supposed to be, like, maybe this is us responding while they're talking and we're getting a bus collision? So they send command 8, and then just immediately afterwards send command 55. So if we're responding to command 8 either when we shouldn't be or when we should be delaying it for some reason, then that might be what's going on. So what is command 8? Oh, a good question from chat. Is the device using the SD core and SPI, SD 1-bit or 4-bit mode? This is in, so the core I'm using, the emulator core that I'm using supports SD in 1-bit and 4-bit mode. It doesn't support SPI mode. And this device is using SD in 1-bit mode. And I checked to make sure nobody was trying to speak in SPI before I used this particular core. Oh, neat. Marshall in the chat wrote the core that I'm using, and it was only extensively tested in 4-bit mode. Yeah, so that, I mean, that could be the issue, but this also might be something that's command specific. I'm going to look up what command 8 is. Voltage check. Yeah, that's weird. So on the real card, they're sending this voltage check command that seems like it should have a response. Command 8, 426. One AA. So one thing I don't understand about the SD card spec yet is, well, I guess whether there's, you know, there are some slots here where it seems like it would be expecting the other end to start responding, but then apparently that's not enough for the next command to actually be delayed. So this has 6, 7, 8 empty bytes here. And if we go over here, the command 8 seems to still be the same, but then Oh yeah, maybe this is just a problem with the core, because this looks like this is when it's supposed to be sending back the command, but this might just be not framing the response correctly. So this is a low start bit and then a high start bit. And this is not the right start bit sequence here. Yeah, okay. Maybe this is a problem with the core. Yeah, Marshall points out that the stopped clock in between I/O chunks smells like an MCU I/O module, and that's definitely the case. This is, I mean, I know what processor they're using. It's the TI Tiva C series, and I'm sure they're just using the quad SPI peripheral for this, and not even using it in quad mode. So, yeah, I mean, none of that is surprising. I just need to talk to this thing. So I think maybe the next step is to look at the core and see how 1-bit mode is implemented and look for bugs in there, because I think that's what I'm seeing. I think that pointer is right, that, yeah, the 1-bit mode doesn't seem to be outputting a properly framed response here. The way the framing works, these ones here are ignored, and anything that's like in between clock cycles, that doesn't matter. We only care about these rising edges of the clock. So these are basically idle bits, and then this is a start bit, but then this bit is also part of the framing. It has to be a 1, and then we see the proper actual packet, and then as indicated by the little X here, that is not right. And then it's trying to detect other start bits, but failing, so yeah. Well, I think that leads to a route forward. I think right now I need to get a bite to eat, but then the next step will be to look through this core and see if I can find bugs in the 1-bit mode. Because yeah, so far I've only been testing this in 4-bit mode, since that's what my, that's what the little dongles that I plug this into on the PC have been using so far. I don't know if I have any adapters handy that use 1-bit mode. I used to have one that I used for reversing. It was like a really old SD card reader that I knew always used 1-bit mode, but I don't have that still, so I think I might just work based on what I'm seeing here, and because it might just be something simple. I think based on what I'm seeing here and like what's actually coming out and what I think should be coming out, I think I might be able to figure this out. But I think that's a task to complete on a less empty stomach. So I think that reaches the approximate conclusion of today's stream. I hope that was interesting. I hope some of you might try your hand at designing your own system on a chip with FPGAs and Python and MyGen, because it's pretty cool. And this particular board that I'm using is pretty inexpensive as far as FPGAs go. This is the Papilio Pro, and it has its own like IDE based on Arduino that you can use if you want. It's also supported really well by all the MyGen based tools. And it's not huge, but it's barely large enough for this design. And it's got 8 megs of SRAM. So it's been a nice little board. It's got a good amount of I/O too. Let's see how Tuco's doing. Oh, I should stop bothering the cat. It seems like he's just into napping right now. I'm gonna go walk to Burritoville and then spend some time hanging out with the source code to this emulation core. And thanks for showing up, everyone. It's always nice to have company hacking on something new. And if you're patient, I'll eventually have a video edited together about this stuff. But in the meantime, I've got the streams, and I've also been, I've been editing together videos, and I'll have another one of those ready to release pretty soon. But that's a bit farther up the pipeline than the stuff that you're seeing right now. So, happy hacking, everyone. Until next time. Oh man, this wireless thing works so badly, it's hard to actually